Welcome to our Big Designs Lab from the FPGA Vhdl lecture series as a part of our FPGA Vhdl course. So in this lab, our aim would be to implement big designs using smaller designs. In the lecture, we learned how to implement big designs using smaller designs by component instantiation. We will be doing just that. To achieve that, let us implement a big design, that is a full adder, using two smaller designs, that is two half adders. Here we will also note the advantage of doing so by the course of this lab. So today we will be implementing a full adder using two half adders. Let us go ahead and do that by clicking on our ISC design suite and opening up our project navigator window. We are welcomed by the familiar new project window. Let us go to file, click on new project. Let us name this as full adder, as we will be implementing full adder today. Click on next, finish. We let the settings be as it is, as we don't want to fiddle around with it. Now this is the new project window that we all know, and here is our project and our FPGA. So let us go to our project and add a new source file to it. This would be a VHDL module. So first of all, our task would be to create a small design and build upon it a larger design. So the small design that we will be implementing is an half adder. So let me go ahead and type half adder as the name of the new source file. This would be the name of the entity that we create. Click on next, finish. Here Xilinx has already written a few lines of code for us. In a half adder, there are two inputs and two outputs. The two inputs being A, B, and the two outputs being carry and sum. So let us go ahead and type that out in the port initialization. Let me call one input as A of the type standard logic, the other input as B of the type standard logic, output as sum of the type standard logic again, the other output as carry of the type standard logic. Remember not to put the semicolon at the end of port, the last statement of port, and put it after the round closing brackets. So here our port instantiation or port initialization is done with the inputs and outputs. Now let us go ahead and create the half adder. We know that in a half adder, we know that sum output goes to A XOR B, whereas carry is nothing but A and B. Here the sum output is 1 when either A or B are 1, but when both are 1, the sum output is 0. So XOR logic gives us that when either of A or B are 1, the output will be 1, whereas when both are 1, the output will be 0. Whereas in the case of carry, we wanted the output to be 1 only when both the inputs are 1 and not otherwise. So we go ahead and type AND. AND gives us the logic of having both the input as 1 resulting in an output of 1. Let us go ahead and save our project and synthesize it. The synthesis takes a little while. The green tick here tells us that our logic was right and hardware could be made out of our logic. Let us go ahead and view the technology schematic. And also the RTL schematic. So here we can clearly see that an AND block and an XOR block is made with our inputs A and B, which is the output that we expect. Now let us go ahead and make our top entity, or make a bigger design using the smaller design of half adder. Let us name this entity as Fulladder itself, as we are going to make a Fulladder. Click on next, finish. Here we have our usual lines of code written for us by Xilinx. Now in a Fulladder there are 3 inputs, A, B and C respectively, and there are 2 outputs, sum and carry. Now let us go ahead and initialize our port according to our inputs and outputs. Say A is an input of type standard logic, B is again an input of type standard logic, C input, or some people call it carry input, is also an input of the type standard logic. There are 2 outputs to our system, sum of the type standard logic, carry of the type standard logic. So our port initialization is done, but here we have to define a few signals, and before doing that we have to define the component half adder which we just created. To do that, we have to type in the keyword component and then the keyword half adder in the exact same manner as we did here. So let us type that, then type the keyword is. So the idea behind this is to make it look similar to entity half adder is, but instead of the word entity we type in the word component. Component half adder is, and we write the same word port opening round brackets. Now here we can go into the half adder component and initialize this with the exact same component as the half adder. So here my half adder had 2 inputs A and B and 2 outputs sum and carry. So I simply repeated the exact same port structure again in the component structure. It is important to note that I wrote the component in between the line architecture behavioral of Fulladder and begin. So any component instantiation must be done in between the architecture opening statement and architecture begin statement. Let us comment this, or rather let us call this as component declaration, as we are declaring what the component is. Then we also need a few signals to connect the sum and carry of both the half adders. Let us call these signals as sum1, sum2, carry1, carry2. These will be the outputs of our half adders, as we are going to use two half adders. Now let us go ahead and call these half adders. When I say call these half adders, it is equivalent of calling a function in C or C++ or Java languages, but here in VHDL we are actually calling a component. We are utilizing the hardware already created in a small project in a larger project. So here we need two half adders to actually realize a full adder, but we don't have to create two half adders. Instead we can create the half adder only once and simply instantiate the component twice. To do that, we have to write the keyword port map opening round brackets. Before doing that, we have to add a label to this keyword port map. Then write the keyword half adder, and then here we write A from our half adder entity list. Then we put an inverted assigns to, that is equal to and greater than sign, and assign this to our entity or signals from full adder. So left is the half adder part, right is the full adder part, or in other words, left is the smaller design part, right is the larger design part. Now let me assign A to A, that is the half adder A to full adder A. This is legal in VHDL. B to B, and let me assign sum to sum1 signal. This is a signal we just created. Carry to carry1. This is again a signal we just created. Also, we don't end the statements with a semicolon. Instead we end them with commas, and the last statement is left as it is with no comma in the end, and finally ending the type of signal is missing, which is standard logic. In our case, now the signal declaration must be done before the component declaration as a rule, and both the declarations are in between architecture opening statement and architecture begin statement. As far as component instantiation is there, we first start with a label. Here I have written a label HA1 half adder 1 colon half adder. Here half adder signifies that this is same as the smaller version of the design that we just created, half adder. So here the entity name is same as the component name. This half adder and this half adder are one and the same. Then we write the statement port map. Then we simply have to map our half adder A to our full adder A, half adder B to full adder B, half adder sum to signal sum 1, half adder carry to signal carry 1. 1 signifies that this is output of half adder 1. Now let us call this half adder again. In HA2, this is again a label that is compulsory. Then we write the keyword half adder and then the keyword port map. Here we map A to C and B to someone. We did this because the output of the first adder will add A and B and give us the result. But we wanted to add A, B and C as our full adder. So we add the result of A plus B using the half adder, and then using another half adder we add the A plus B result to our third input, that is C. Then sum is the final output that we want. I'm calling here sum2, which is a signal. Carry is carry 2. Again, these statements are separated by commas, and the last one is left as it is. Now our component instantiation of half adders are done. We need to end the component before moving ahead, otherwise this might lead to an error. So whenever we start a component declaration, we must always end it. So our final sum output would be sum2, and our final carry output would be carry 1 or carry 2. Now again let us go ahead and synthesize our project. This time we didn't get any warnings as such. We got a green tick signifying that hardware could be created out of our project. Let us go ahead and view the technology schematic. Click on this button. Here we have our two blocks. Let us go ahead and view the RTL schematic. Where we can clearly see the two half adder blocks and the OR we did in between. When we double click on the half adder, we can see the AND gate and XOR gate we used inside the half adder. So we just created a full adder, two big designs using smaller design, that is half adder. Here we have used label HA1 and HA2 to signify that these are two different blocks with two different names. Labels are nothing but names given to a certain block. They are used only when we do component instantiation. That's it for today's lab. See you next time.